Today, I'm going to talk about our recent work on runtime safety for planning and control from images. Many of the most impactful applications of autonomous robotics are safety critical. To act in these settings, a robot typically has an autonomy pipeline. We get information from sensors about the environment and the robot state. We then use this information to compute a plan, and the plan computed also depends on the dynamics model used to approximate the system. We'll then use feedback control to stabilize around that plan, and then close the loop. A growing trend is that to improve performance, many of these components may be learned from data, especially perception, where deep learning has made major strides. However, these learned components can be quite prone to error, which can exacerbate the fragility of this pipeline. For instance, our perception system may fail if it is evaluated out of distribution. The same goes for the dynamics model. And to make matters worse, these errors quickly propagate downstream and can amplify existing errors, which can compound and then lead to catastrophe. Since these errors are so coupled, I argue that for truly safe autonomous systems, we really need a unified analysis of the system from sensors all the way down to control actions. In this work, we take steps towards such a unified analysis by tackling what we refer to as the safe output feedback motion planning problem. This problem entails planning trajectories that can be safely stabilized when controlling from images using a learned perception module. This is a long-standing problem related to several areas of research. There's been a lot of work recently in image-based control from the ML community, but while empirically impressive, these methods tend to lack safety guarantees. There has also been work on the control side, but most of these methods require strong assumptions, such as linear dynamics, or requiring the state to be invertible from a single observation. More traditional work in planning under uncertainty is also related, but generally assumes perfect state information or requires approximations which can compromise any safety guarantees. We aim to alleviate some of these restrictions in this work. We consider nonlinear systems controlled from images with a learned perception module, and the state will be estimated dynamically, foregoing the invertibility assumption in prior work, and we have guarantees at runtime. We consider in this work uncertain nonlinear systems x dot equals f of x plus bu perturbed by model error w dyne. We assume that we do not have direct access to the underlying system state at runtime, and instead we are given images which are a function of the state x as well as a context vector theta. For instance, in the context of navigation in an obstacle field, theta could be the map. We assume that the system is incrementally exponentially stabilizable and observable, which we will need later for our contraction-based convergence guarantees. While strong, these properties still apply to many under-actuated systems like cars and quadrotors, as we'll show later. Moreover, in this work, we restrict our attention to simulated images that are noiseless. We assume that we know the nominal dynamics, that is, we know f and b, as well as an upper bound on the model error w bar. Critically, however, we do not know the perception map h. We are, however, given a dataset of x, theta, and corresponding y's to train a perception module, as well as an IID validation set collected nearby this training set. Our goal is, given the learned perception system, to plan a trajectory that safely reaches the goal at runtime when only using images and the learned perception module to control the system. The key challenge in achieving such guarantees lies in bounding all of the error that the system is subjected to, and then propagating all of those errors through the entire autonomy pipeline to determine how that will impact where the system will potentially end up. I'll now overview our method. The key insight of our approach is that we can leverage control theoretic tools from contraction theory to take an estimated upper bound on the perception error and propagate it all the way down to low-level tracking control, giving the desired unified safety analysis. Our method has an offline and online stage. Offline, our method uses the training set to train a perception system, which I'll break down in just a moment. We then use the validation set to estimate an upper bound on the perception error with a user-desired probability of validity. In parallel, we design stabilizing controllers and convergent state estimators using contraction theory. Then, we bound how the perception error degrades the performance of the downstream controller and estimator, giving tubes where we know the system will remain at runtime. Then, at planning time, we use these tubes to compute a plan, which can be safely tracked according to these tubes. Online, we observe high-dimensional image measurements, y, and the context vector theta. This gets passed into the learned perception system, which is trained to predict the subset of the states, x observable tilde. These are the state indices directly observable from a single image. For instance, for the navigation problem, this will be the pose but not the velocities. And as the learning is inevitably imperfect, this will introduce errors which we will need to bound later. To get around this partial observability, this prediction is fed into the contraction-based state estimator, which dynamically estimates the full state, much like an EKF. We refer to this estimate as x hat. Finally, we feed x hat into the contraction-based tracking controller, which stabilizes around the plan, assuming the system is at the estimated state. This is called output feedback control. I'm going to go over the offline components in more detail, starting with contraction. For clarity, I'm going to avoid going into the deep mathematical details of contraction. You can find that in the paper. Instead, I'm going to focus on what it provides us at a high level. When designed for a nominal system with no dynamics or perception error, a contraction-based controller is guaranteed to converge exponentially quickly to any dynamically feasible plan. By exponentially quickly, I mean that the error in tracking the plan shrinks at some rate lambda c over time. The same properties hold for a contraction-based state estimator. And these contraction-based controllers and estimators can be efficiently designed for control affine systems via convex optimization. However, when error is introduced to the controller and estimator, the state and the state estimate are going to be perturbed, and will instead remain in a tube around the nominal and true trajectories, respectively. Crucially, the size of this tube scales with the size of the disturbance. So to have valid tubes to ensure downstream safety, we first need to get a valid upper bound on all of the errors input to the system. So let's collect the sources of error in our system. We have two sources of error. The first is the dynamics model error, which we assumed upfront to know an upper bound on. A more subtle source of error lies in the mismatch between the true state and the state estimate. Suppose we're trying to track the green trajectory here. Recall that our controller decides which control to take based on the estimated state. If there is a large error between the estimated and the true state, then the resulting control mismatch may actually destabilize the system. Bounding this term is one of our key contributions. The magnitude of this mismatch depends on the magnitude of our state estimate error, which is, if you recall, driven by the error in the learned perception module. So we need to upper bound this learning error everywhere that the system may reach at runtime. Our approach is to select a trusted domain D, where we want to estimate a valid upper bound, and then, at planning time, ensure that we always remain in this set D where that bound is valid. We want to select a D where the perception error is low, so that the resulting tracking tubes are going to be small enough. In particular, we will select D to be a neighborhood of the training data where we expect the model to be accurate. We then estimate an upper bound on the perception error, WNN bar, using the IAD validation data, using a probabilistic approach based on extreme value theory. For details, you can see the paper as well as our prior work, but the key part here is that the user can select a desired probability beta such that the estimated bound overestimates the true perception error, thereby giving a valid upper bound. Selecting a large beta will scale the conservativeness of the resulting bound. Finally, we can convert the upper bound on state estimate error into a bound on W mismatch by estimating a Lipschitz constant via extreme value theory with the same probabilistic guarantee. Now, given our upper bound on the tracking error derivative, dc dot, we can just integrate in time to give an upper bound on the runtime tracking error. And since this is just an integration, it is fast to do and gives us our desired error-informed tracking tubes. Moreover, since contraction theory lets us calculate these tubes for arbitrary feasible trajectories, it can be used to constrain planning to ensure the system remains in D at runtime. So that's exactly what we do. We modify a Keynote dynamic RT with the key change that we also grow trajectory tracking error tubes around any candidate extension within the planning tree. We also add some additional constraints. One, that the tubes themselves are collision-free. This ensures that the system will not collide when attempting to stabilize around the plan. And two, that the tubes are fully contained inside the trusted domain D. This ensures that the tracking and estimation tubes are in fact valid, since otherwise we may underestimate the perception error outside of D. This brings us to our main result, which is that if all of the EVT estimated constants are valid, which assuming independent samples will hold with probability beta squared, then the true system will remain safely inside the computed tube at runtime. We provide an overview of our experiments on safe output feedback motion planning with learned perception modules on a 4D non-holonomic car, a 6D planar under-actuated quadrotor, and a 14D acceleration-controlled arm. In the following, to demonstrate the need in planning to both stay within the trust domain D, as well as consider the destabilizing effects of state estimation error, we compare with two common baselines. B1 uses our computed tracking tubes, but leaves the domain D in which the tubes are valid. B2 ignores state estimation error, assuming that the system will obtain perfect state estimates in execution, and computes its tracking tube accordingly. We first show our results on the car. Our goal here is to steer from the start to the goal without crashing. Note that the perception system is only trained on Y positions between negative 2.5 and 2.5. We will first animate two plans generated by our approach. On the top left, we plot our trajectory tracking tubes in gray, the plan in green, and the executed trajectory in magenta. On the bottom left, we plot our state estimation tubes in gray, the executed trajectory in magenta, and our estimate of it in cyan. On the right, we plot the observation that the car sees at runtime. We see that our approach can reliably shrink the tracking error, as well as keep the state estimation error low, and that the executed trajectory and the estimated state trajectory both stay in their corresponding tubes. This enables our method to reach the goal. We obtain a similar result for this second rollout that you see over here. In contrast, we see that the baselines will both fail. At first, B1 does fine, but recall that B1 ignores the trusted domain, and eventually it moves beyond the domain where the perception system is trained. And this causes the state estimate to rapidly diverge upon leaving the training distribution. This in turn destabilizes the feedback controller, causing it to act unpredictably, and causes the system to crash into the wall. A similar result happens for B2. B2 ignores the state estimate error in planning, and it also moves beyond the training distribution, leading to a similar result where we crash into the green obstacle. Now, we show our results on the quadrotor. Note that the perception system is only trained on X positions between negative 4.5 and 4.5, and on Z positions between 0.5 and 4.5. We will first animate two plans generated by our approach. On the top left, we plot our trajectory tracking tubes, the plan, and the executed trajectory. On the bottom left, we plot our state estimation tubes, the executed trajectory, and our estimate of it. On the right, we plot the observations that the quadrotor sees at runtime. Like before, we see that our approach can reliably shrink the tracking error, as well as keep the state estimation error low, and that the executed trajectory and the estimated state trajectory both stay in their corresponding tubes. This enables our method to reach the goal safely. And again, we obtain a similar result for the second rollout that we show over here. In contrast, we see that the baselines will both fail. Both B1 and B2 end up leaving the domain where the perception error is low, and this in turn causes the state estimate to diverge, which again in turn destabilizes the feedback controller, and this leads to crashes in both of these cases that we show over here. Finally, we show our results on the arm. In this experiment, our goal is to exploit the state estimation tube for guarantees on active perception. Here, we have a KUKA arm grasping a duck, and it has unknown orientation relative to the end effector. We want to improve our estimate of this orientation by moving the arm around to get better readings, and at each time step we are going to observe an RGB image of the scene and the arm's joint angles, which we assume can be measured exactly. Specifically, we want to use our method to plan a trajectory for the arm that can guarantee that the orientation error at the end of execution is within a 0.1 radian tolerance for each of the three Euler angles that need estimating. In essence, we want to use our perception error bound to guide the planner towards regions where the perception error that will be experienced will be small enough in order to reach the desired estimation accuracy. We compare with two baselines in this example. The first is a simple baseline, where we don't move the arm at all and just run our state estimator passively. The second baseline is B1, where we leave the trusted domain. We will first show the result of the no motion baseline, which we call B3. Note that while our estimator can shrink the state estimation error to some extent, we cannot satisfy the 0.1 accuracy tolerance. This is due to the error in the perception system at this configuration. In contrast, our method, starting from the same configuration, moves the arm around in a way that finds regions of the space which have lower perception error, and this enables us to satisfy that 0.1 tolerance. Note that we also remain within our state estimation error tubes, where we have plotted a projection of these tubes onto each Euler angle in gray. Finally, we compare with B1, which leaves the trusted domain. We see at first that the error is reasonably good, but then it plans to move the arm too close to the camera and the duck falls out of frame. This confuses the perception system since it now cannot accurately invert the duck's orientation since it cannot actually see the duck. This corresponds to high perception error, which destabilizes the state estimate and causes B1 to fail to satisfy that 0.1 error tolerance. Before I conclude, I want to talk about some dirty laundry. The biggest limitation to our approach is the fact that we need a large dataset of labeled ground truth state and image pairs, which can be extremely difficult to get in the real world. I see that there are maybe two options forward here. One is to train in many domain randomized simulated environments where the labeled data is plentiful to increase the likelihood that the perception error on real images is small, and then obtain a coarse bound on that error using a small dataset of real images. Another is to simply verify latent space planners instead, which do not require ground truth state image pairs, and this is the subject of current work. Another drawback is that EVT gives asymptotic results in the sense that the probability beta is only guaranteed to hold in the limit of infinite samples in the validation set. So in the future, we're going to look more into methods for finite sample error bounds to get around this. Finally, we also assume here that the map theta is known, but it may be possible in future work to simultaneously estimate theta as well as x, assuming that theta remains observable. So let me conclude with a recap. For safe planning and control from images, we need to bound the perception error, determine how it affects downstream tracking, and then use that knowledge to in turn design plans that by construction can be safely tracked. Our solution is to leverage extreme value theory to bound the error, propagate it to low-level control via contraction theory, and then to use decontraction-based tubes to constrain a planner to return safely trackable plans. Thanks for your attention.